Okay, today I'm going to talk about section 2.4. This is called implicit differentiation. A little warning, this is a topic that usually at first seems quite strange. I will tell you with a little practice, this tends to be something that mechanically ends up being relatively easy for students, but at first it looks a little bit strange. So don't panic if you know this doesn't come to you all at once. Okay. So what we're going to do first is we're going to contrast what is called implicit differentiation with what we've been doing so far, which you could guess is called explicit differentiation. So this idea of y equals and then x stuff and then taking the derivative of y in terms of x, that would be explicit differentiation. Implicit differentiation, ultimately we're going to use it on things that are not necessarily functions. You know, there's basically x's and y's mixed into the equation, and it just makes it a lot easier when we're given these types of situations. Okay, so in this first one, we are going to go ahead and take a look at this explicitly. X squared plus y squared equals 1. That is basically our unit circle. Has a center at 0, 0. The radius is 1. And ultimately, we're going to be interested in writing tangent line at these 2 points. 1/2 radical 3 over 2 and 1/2 negative radical 3 over 2. Okay? Now, with our current tools, we can do this. But what we have to do is we have to write this equation as two different functions. So we're going to write this as a top equation. So if we solve this, we're going to get y equals, and then it's going to end up being plus or minus the square root of 1 minus x squared. So the top is going to be the positive of that. Okay, so we still have to look at this as a function. So if I want to look at the top of this, I can find the derivative of the top, but I have to deal with this as two separate functions. Top function, bottom function. So we're going to do this the way we've been doing this so far. So we'll write this to the 1/2 power. Now when I take the derivative of this, I do have to use chain rule. Okay, so remember chain rule is when we have a function plugged into another function. So our outer function is the square root function. The inner function is the 1 minus x squared. So the 1/2 will come down in front, negative 1/2. Everything inside stays intact. Then we chain out the derivative. Okay, so there's our derivative. Now, because I'm working with this, you know, normally when we're just stringing out derivatives, we just leave it like that. But since we're working with this, we want to simplify it. So let me point out the negative 2 cancels with the 1/2. That leaves me with a negative out front. We're going to have an x in the numerator, and then that negative exponent is going to move that to the denominator as 1 minus x squared. Okay, so that's the derivative I'm going to work with here. So if I want to find the tangent line here, I need this slope. So y prime of 1/2 is equal to negative 1/2 over 1 minus 1/2 squared. So that's 1/2 over 1/2 squared is 1/4. So this will be 1 minus 1/4, so that's 3/4. Now, let me point out to you that radical 3/4 is radical 3 over 2 because, of course, the square root of 4 is 2. And now we can multiply top and bottom by 2, and I get 1 over radical 3. I don't care if you rationalize this. Leaving this slope as 1 over radical 3 is perfectly fine with me. If we did rationalize it, we would get radical 3 over 3. But however you want to express that is fine with me. Well, let's just leave it 1 over radical 3. Okay, so my tangent line here would be y minus radical 3 over 2 equals slope of 1 over radical 3, and then x minus 1/2. And that is our tangent line I have drawn up there. Okay. Now we have to do this for the bottom half. So the bottom half, okay, so let me go ahead and erase and we'll start talking about the bottom half. Only thing with the bottom half is when we do the plus or minus when we solve for y here, the top we do the positive and the bottom we're going to do the negative. Okay, let's talk about the tangent line there on the bottom. So same thing, we have y equals, and then this time as I said, the negative. Let's rewrite that as negative, parentheses, 1 minus x squared to the 1/2 power. Let's take the derivative of that. So very, very similar to what I had before, of course, except this time we're going to end up with a positive, which you can kind of see where this is going, hopefully. So that's going to give us an x in the numerator, and then we'll move this to the denominator with our radical. Okay, and then once again, we'll plug in the point 1/2. We get 1/2 over square root of 1 minus 1/2 squared. By now, I think we realize we're going to get the same thing we got last time numerically, except it'll be positive, 1 over radical 3. So our bottom equation, surprise, surprise, is the same except positive, which makes sense with what we're seeing here. Oh wait, I made an error. So this one's the positive one. What happened on the last one? I missed, on the last one I had the negative out front, so that would have been negative of, sorry about that, so that should be a negative out front. My bad, so go back and fix that if you will. So on the last one here the negatives cancel, giving us positive. On the last one, we have the negative out front. Let me rewrite that so it looks a little better. And so now I'm demonstrating why this is not the best method, which was my point all along. I planned on showing you that this is not the best method. Oh, goodness. Falling apart here. This is 1/2, that's 1/2. And that one's negative. Okay, now we got it right. Okay, so if I ask you to find the tangent line length, so you could do that. Obviously, it's a lot of work. We have to break this into 2 separate functions. What I want to show you is a new method, which is called implicit differentiation, to do this instead. Okay? So let me show you that. Okay, so let's talk about taking the derivative of this equation, x squared plus y squared is equal 1. So with implicit differentiation, we do not solve for y, we leave it as is. So basically, implicit differentiation allows us to take the derivative of things that are non-functions, okay? So here's the idea. When we get into taking the derivative, the thing that we have to understand is when I say I want the derivative of dy over dx, that means I'm taking the derivative of y with respect to x. What's important to realize is that this means that y is the independent variable, and x is the dependent variable. And it's important that we keep that straight because the way these things are going to behave are very, very different. So in other words, what that means, generally speaking, is y is some term of f, or excuse me, of x. And so if kind of in this context, the way we want to look at this is, whenever I see y, it's defined in terms of x stuff, okay? So what that means is if I ever take the derivative of y, I've got to use chain rule because it's got its own little function inside. So when we do implicit differentiation, dy over dx, the whole idea is that y is its own function of x. So every time I deal with y, I have to do chain rule. Okay, so for instance here, okay, take the derivative of x squared. That's, as always, just 2x. That is because this is the independent variable. And then when I take the derivative of this, I'll call this plus 2y. But since y has its own little function in there of x, I've got to take the derivative of that, dy over dx. I don't know what that derivative is. I don't really care what that derivative is, but I just do the derivative as dy over dx. Now, what I'm trying to find is I'm trying to find that derivative, dy over dx. So I'm going to solve for that. So 2y dy over dx is equal negative 2x. And now we've got dy over dx is equal to negative x over y. Okay, so now at this point, this is my derivative. Now the one thing nice about this derivative, and I just want to remind you that our other derivatives were y prime equals, by the way, y prime dy over dx, same thing. We had the top, which was the negative x over square root of 1 minus x squared, and the bottom we had y prime is equal to the positive of x over 1 minus x squared. So what you should see here is this is actually the same, because y, if you remember when I solved that, was the negative, the positive on the top and the negative on the bottom. So this still makes sense, but it's dealt with just in terms of x and y. So the only difference here is, so you can see that's a lot more, less work than all the work I had to do to both of those. So now the only thing is, when I want my derivatives for implicit, I need both the x and y. So the notation here, and this is one of those things you have to get used to, the notation is dy over dx, and then I draw a line like this, and then I show I'm plugging in the 0.1/2 radical 3 over 2. So I plug that in. So this is the top point. So I need to also include the y. So this will be negative 1/2 over radical 3 over 2. And you see what happens here. The 2's are going to cancel. And I get negative 1 over radical 3. And you can see that gives us the same thing. And if you remember I made that mistake, this is a lot easier to do it this way. Okay? So implicit differentiation just sort of streamlines that process. All right. So let's talk about some other things with this. So this is our derivative here. And by the way, we can do the same thing with the bottom. A couple of things. First of all, one of the discussions that we might have is, where does this function have a horizontal tangent line? So when do we have horizontal tangent lines? This is something we start talking about in class. So we know we have horizontal tangent lines when our derivative is 0. Now the great thing about this is I can actually see where those horizontal tangent lines are. I can see there's one at 0, 1. I can see there's another one at 0, negative 1. But let's see what that looks like algebraically. So if I have a horizontal tangent, okay, that means that this is equal to 0. Now, if I get a fraction equals 0, what that means is the numerator has to be 0 when the denominator is not. So what that means is x has to be 0. So right away we see that that's what we find there. Now, of course, to get the y, we're going to plug 0 in, and we can see very quickly that if I plug 0 in for x, I get y squared is equal 1. So we get y is equal to plus or minus the square root of 1, which of course is plus or minus 1. So I get 2 points, 0, 1, that's the place where it's horizontal on top, and 0, negative 1, which is where it's horizontal on the bottom of that graph. Okay? Now, we can do the same thing with vertical. You can see we're going to have vertical tangent lines at 1, 0, and negative 1, 0. Now, when do we get vertical? When does a vertical tangent line happen? Okay, well, let's think about that. If that goes vertical, what I'm really saying is it has an infinite slope. How do we get an infinite slope? Well, we have basically something that's approaching 0 in the denominator. Right? If I take 1 and divide it by something getting closer and closer to 0, that number explodes and gets closer and closer to infinity, or grows without bound, I should say. Okay, so if we have a vertical, and you're going to see these mixed in, so just a refresher, horizontal would be the numerator 0. Vertical means dy over dx does not exist. And we talked about that when we talked about differentiability. Why would this not exist? Because y is equal to 0. And now we play the same game again. We plug 0 in for y, which is going to give us x squared is equal to 1. So that means we get x is equal to plus or minus the square root of 1, which is just 1. And I get my 2 points, negative 1, 0, where it's vertical over there, and 1, 0, where it's vertical over there. Okay, so this is implicit differentiation. All right, let's do a couple more examples. And if you're sitting here thinking, you know what, I don't want to learn a new method, I'm just going to always go back and solve. What I'm going to do on these problems are problems that you absolutely have to use implicit differentiation, because you cannot express it as a series of functions of x. Okay. Okay, so example 2, we're given a different equation, x squared minus xy plus y squared is equal 1. And we are going to do these three things with this particular equation, not a function. Now, the last one we did, x squared plus y squared is equal 1, because we knew that was a circle, we could draw this. This is not something we're necessarily going to know. and that's okay. That's pretty common with these implicit derivatives. We don't necessarily know what these things look like. So the first thing we're going to do is we're going to find the derivative. We do have to do that implicitly. Then we're going to find the slopes of the tangent line at x equals 0 when x equals 1. And then finally, we're going to find the coordinates of the graph for the two vertical tangent lines. Okay, so let's start off with part A. Okay, so part A, we're going to take the derivative of this. Now, the one thing I want to remind you, we're taking the derivative with respect to x. X is the independent variable. That means x behaves the way it normally does when we take the derivative. Y is a dependent variable, which means it's its own function of x. So every time I take the derivative of y, I have to do chain rule. Okay, so let's go ahead and do that. So the derivative of x squared is going to be 2x. Now this minus, you have to be very careful with this. When we take the derivative of this, we have to do product rule. So ultimately, when I take the derivative, that minus will be we're going to have to distribute through the product rule. So I would say put this in parentheses. Okay, so now let's do this. The derivative of x is just 1. We copy down the y. Plus, copy down the x. Now, what's the derivative of y? Well, it's 1, but then because of chain rule, y prime. We'll just call it y prime here to save ourselves the trouble of writing dy over dx. Means the same thing. And then here, when we take the derivative of this, just like it's x, 2 comes down, y to the first, and then because of chain rule, we get y prime. Derivative of 1 is 0. Okay? So now what I want to do is I want to solve for y prime. So I've got a little bit of simplification to do. So 2x minus y minus x y prime plus 2y y prime equals 0. Now ultimately what I'm trying to do is solve for y prime. Now this little algebraic trick is one we did with inverse functions. You're going to see this a lot. We have two terms that have the thing we're trying to solve for, y prime. Any term that has the thing we're trying to solve for, we're going to leave on one side. Every term that doesn't have the thing we want to solve for, we're going to push on the other side. So that's going to look like this. Negative x y prime plus 2y y prime. This we're going to add to the other side. This we're going to subtract. Okay, now what that allows me to do, since everything over here has my y prime, I can factor that out, and I get y prime is, y prime, parentheses. By the way, I'm showing all the steps here. Once you get this down, you might not need to show all of these steps. So anyways, I factored out the y prime, leaving with negative x plus 2y. If you want, you can call this 2y minus x. That's maybe a little bit cleaner. It's really up to you. Now to solve this, I'm just going to divide both sides. And just for the sake of simplicity, let's call this 2y minus x. We know that these are the same thing. Our derivative is just going to be a little nicer this way. And there we go. That will cancel. We're left with y prime equals y minus 2x over 2y minus x. And that is our derivative in terms of x and y. Okay, so let's record that so we can go on to the rest of this. So our derivative here, y minus 2x over 2y minus x. Okay, let's move on to part B. So I wrote y prime up there. Now we're going to find the slopes of the tangent lines. Notice they're not actually asking me for the tangent lines, they're just asking for the slopes of the tangent lines. Now the thing I have to realize here is that I'm just giving you the x's. I need x and y here. Now the one thing we have to remember about these is if we're ever looking for, like we have an x value and we want a y value, don't go to this equation. Always go to the original. So what we're going to need to do for part B is, first of all, we're going to have to find the y that goes with 0 and the y that goes with 1. So start off with 0. Everywhere I see an x, I'll plug in 0. And luckily, right, this ends up giving me y squared is equal 1. So y is equal to plus or minus 1. So what that means is we have 2 points where x is equal to 0. We have 0, negative 1, and 0, 1. Okay, so 0, so let's go ahead and plug that in our derivative. So we have two tangent lines, because remember these things, you know, they're not necessarily functions, so that they don't pass vertical line tests. This has a point at 0, negative 1, and 0, 1. So y prime of 0, negative 1. By the way, this is another new notation you can use. a little bit different than the dy over dx with the line. I'm going to plug this in here. So everywhere I see a y, I'll put the -1. And everywhere I see an x, I'll put a 0. And what I get is a -1 on top, -2 on bottom, so that's 1/2. Now, if they did ask us to write the tangent line, that'd be pretty easy. I would just use this point, and there you go. But all they asked for is the slope of the tangent line. So this one, that's one of them done. And now we're going to do the other one, okay? So that's going to be 0, 1. So everywhere I see a x, I'll plug in 0. Everywhere I see a y, I'll plug in 1. So 1 minus 2 times 0 over 2 times 1 minus 0. So this is equal to 1/2 as well. And there you go. Okay, so we're done with this one. Let's move on to x equals 1. So we're still on part B, right? We just did the tangent lines for our 2 points where x equals 0. So 0, -1, 1/2, and 0, 1, which also was 1/2. Okay. Okay, so let's go ahead and do x equals 1. So that means everywhere I see an x, I'll plug in 1. So 1 squared minus 1 times y, that's going to be y, plus y equals 1. So, oh, this is y squared. So what we have is a quadratic here. So if we don't have a calculator, we're not going to be able to graph this. We're going to have to hope this factors. So let's rearrange this in a way that is factorable. So this is going to end up being, actually this is going to be nice because if I subtract the ones from both sides, those are going to zero out. So I'm going to get y squared minus y equals 0. Factor out the y. And now I know that if I have two things multiplied to be 0, one of them, at least one of them has to be 0. Okay, so y equals 0, y equals 1. So once again, we get 2 points. So 1, 0, and 1, 1. So now I'm going to do the same thing again. Plug 1, 0 into our derivative. Okay, so 0 minus 2 over 0 minus 1. -2 over -1, that will give us positive 2. And now y prime of 1, 1. So that's going to give us 1 minus 2 over 2 minus 1. So this is going to give us -1 over 1, so that's -1. And that is my two slopes there. Okay, so now we're done with this one. Let's go on to the vertical tangents in part C. Okay, part C, we want to find the coordinates on the graph for the two vertical tangents. So once again, the key here is, since we're talking about vertical, we know that from our discussion about differentiability, that means our derivative doesn't exist. So what that means here is, so if y prime, which is equal to y minus 2x over 2y minus x, does not exist, right? What that means is 2y minus x equals 0, okay? So now what I realize is I have two unknowns. And this has come up quite a bit in this class. When I have two unknowns, that means I have two equations. So I have this equation here. So let's go ahead and solve this. Let's solve this for, so we don't have to deal with fractions, we'll call this x equals 2y. So I'm just adding that to the other side. So now we have one equation. In these problems, you always have to remember, if we're ever looking for another equation, it's always back to the original. So this is our other equation. We've got to then take this. So whether it's values of x and I want y like we had in this problem here, or whether it's a problem like this where I need two equations, you go back to that original. So what I'm going to do is I'm going to take this and plug this into my original. So this is going to be 2y squared. So everywhere I see an x, I'm just plugging in the 2y. Minus, so x is 2y, and then we have this y, plus y squared equals 1. So I've got some simplifying to do here. So 2y squared is 4y squared, minus 2y squared, plus y squared is equal to 1. So 4 minus 2 is 2 plus 1, that's 3. So this gives me 3y squared is equal 1. So now I have y squared is equal to 1/3. So I have y equals, and then when I take the square root, I gotta remember the plus or minus. Okay? And there we go. So this is the y. Now we need the x. By the way, I don't need you to do anything with this. So the x, we're going to plug it in up here. So realize this is 2 points, right? So we have one, let me just write this out. So y equals negative and y equals positive of the square root of 1/3. Okay, so now we want to get the x. So what that means is that to get the x, I just have to multiply these by 2. So I'm going to have negative 2 radical 1/3. And by the way, I don't need you to simplify these. These are perfectly fine. These are perfectly simple. And then the other one will be y will be negative 1/3. So that's my first one. So this is my y. Plug that in to get my x. And then my second x, I'm running out of room here. The second point would be 2 positive of 1/3, and then radical 1/3. So those are my 2 points where it's vertical. In these types of problems, you're going to be doing this whole thing with the vertical and horizontal quite a lot. So I want to remind you, these are typically fractions. If it's a question of when it's vertical, that means we have a 0 in the denominator. If it's a question of being horizontal, that means the whole thing is equal 0, which means the numerator is 0, but the denominator is not. Okay, I am going to go ahead and break this video into 2 parts because I know this is kind of running kind of long. I'm going to do a couple more examples here, and then on the next video, part 2, I'll call it. So let's officially name this part 1. We're going to be doing the double derivatives of these things. Okay, so this is part 1. Okay, I'm going to do a couple more examples, and then we will call it a day. Okay, example 3, we have the equation 4x squared plus y squared minus 8x plus 4y plus 4 is equal 0. On the last example we did the coordinates of vertical tangents. This time we're going to find the coordinates of horizontal tangents. First thing I need to do is take the derivative of this thing. So once again, we're going to take the derivative implicitly. X behaves the way it should. The y, every time I take the derivative of y, I have to do chain rule. So this will be 8x plus, take the derivative of it like it's a x, 2y, and then we have to remember the y prime, minus derivative 8x is 8, plus the derivative of 4y is 4, y prime, and this goes to 0. By the way, a common error here is people sometimes forget to take the derivative of constants, getting 0. Okay, so now I'm going to leave this on the left. And these I'm going to move to the right, so let's add the 8, subtract the 8x. And now we can factor out the y prime. This marker's running out. And then I can divide by the 2y plus 4. I'm going to go ahead and just show that. And that's going to give me 8 minus 8x over, and then 2y plus 4. Let me point something out to you. I can actually simplify this. Notice I can take 2 out of all these terms, so I can write the top as 2, and then 4 minus 4x. And on the bottom, I can rewrite this as 2, and then y plus 2. So these 2's will cancel. So now we have our derivative dy over dx is equal to, and then 4, yeah, this is pretty much toast. 4 minus 4x over, and then y plus 2. Okay, so I think simplifying here is a good idea because then we have to work with it. Okay, so let's talk about finding horizontals now. So since we already did the work here, let's erase this, and I'm going to get myself a new marker. Okay, so now we want to find when we have horizontal tangents, what coordinates. So keep in mind, a horizontal tangent means my slope is 0, so my derivative is 0. So I want to know when dy over dx is equal to 4 minus 4x over y plus 2. I want to know when that's equal 0. If I have a fraction that's equal 0, it means the numerator is equal 0. So this means the numerator is equal 0. So 4 minus 4x has to be 0. Okay? So, well, that you can pretty much see this. This means that x is equal 1. Okay, now they do want the coordinates here, so keep in mind if we're ever looking for another point, we're always going back to that original. So everywhere I see an x, I'll plug in a 1. So this will be 4. That, of course, is just 1, so we'll leave it here, plus y squared minus 8 plus 4y plus 4 equals 0. Now we want to solve this, so we've got to do a little simplifying here. Y squared plus 4y. Let's see, nice again. So that's going to be 0 here. So I can factor out a y plus 4 equals 0. The old 0 product property, if I have two things multiplied to give me 0, it means at least one of them is equal 0. So y equals 0 or y equals negative 4. So our two coordinates where we have a horizontal tangent are 1, 0, and 1, negative 4. Okay. I'm getting tired here. I'm sure you are too. I'm going to do one more example, and that will be it for part 1. And then I'll put out a part 2 video where we'll do the double derivative, and I'll probably do some more examples because I think this is one where it's good to see a couple looks at this. Okay. Okay, one last example. In this one, we're going to write a tangent line. So here's our equation, and here's the point. So of course, what I need is a slope. So I've got to take the derivative. I'm going to take the derivative implicitly. So we'll start off with this. I want to point out that is product rule. So let's take the derivative of x squared. That's going to give us 2x. Copy down the y term. Plus, now we're going to switch it. So take the derivative of the y term. That'll be 3y squared. And then because of chain rule, that'll be y prime. Copy down the x squared. Plus, derivative of 2y will be 2. Y prime is equal, and then 3. Just a little hint here. If you ever get confused with the y's, the x's just take the derivative like we've been doing. The y's just take the derivative like it's an x, but then make sure you have a y prime multiplied by it. So for instance, when I took the derivative of y to the third, 3y squared just like it was x, and then just put the y prime next to it. Okay, so we are going to isolate these two terms that have the y prime. Now let's get the x over here. And plus 2y prime. And then this will subtract that to the other side. Okay. If you don't mind, I'm going to skip some steps here. So what I'm going to do here is I'm going to factor out the y prime, and then I'm going to divide by that term. So what I'm going to end up getting here, and if you need to write it out on your own, you go ahead and do that. This is one of those things that with time, you'll get better at this and you'll start sort of skipping steps. But you show as many steps as you need. I will tell you, I always need that first step, and then whatever arithmetic or algebra you do in between is up to you, and then that final step. Okay, so 3 minus 2, okay, and then 3y squared x squared minus or plus 2. And you know what? Normally we go alphabetical order here, so that's what I'm going to do here too. So this is going to be 3x squared y squared plus 2. And there's our derivative. Okay? Let me double check that. Okay, looks good. So now's our derivative, and now all we need is a slope. So I'm going to take this point, 2, 1, and I'm going to plug it into this. So that's going to give me 3 minus 2 times 2, and then 1 to the third, that's just going to be 1. In the denominator, 3, 2 squared, that's 4, and y squared, that's just 1 plus 2. Let's simplify this. let's see, 3 minus 4, so that's negative 1 in the numerator. In the denominator, 12 plus 2, that's 14. And there is our slope. So the equation we're line, the rest of this is pretty easy. Y minus 1 equals negative 1 over 14, x minus 2. And there you go. Okay, so that's implicit differentiation. Sorry for the extra long video. We will have a part 2, but I will tell you that's probably going to be a much shorter video. And this is one of those things that is going to take practice. It's usually kind of a shock at first. It seems quite strange. There's a lot of algebra, but you're going to find with time that the mechanics here are really not that bad. So that's 2.4, implicit differentiation, part 1.